Okay, physical science. I'm super sorry about this glare. I could get rid of it, but then my arm's in there. It's not going to work out. I made a worksheet to practice some more total force, and we didn't get to all of these in class, so I wanted to go over them here. And if you're struggling with this, I want to help you. So we're going to start. We did the front side completely. Maybe I'll make another video for those who missed that. I want to start on the back side, number 6. Quick review. We've got our total force, and that's going to be equal to our mass times acceleration. All right, our unit on force is newtons, our unit on mass is kilograms, and our unit on acceleration is meters per second squared. So this isn't constant velocity. This is somebody who's either speeding up, changing direction, or slowing down. Someone traveling at a constant velocity, there's no net force. There's being force applied, but there's no net force if there's no acceleration. Okay, that's quick review. The second part of this is that the applied force, so force applied. Oh gosh, guys, my handwriting or my spelling's worse on here too. Your force applied, subtract your friction force, because that's where we're going, and that's going to equal your total force. That's this guy up here. Okay, this is your total force. We'll give him a little T. This is pretty much all we're using to figure this out. Now, quick recap, there's 2 kinds of friction. Static friction, which is when something is not moving. And sorry, that just try to ignore it. I'm trying. And we have kinetic friction when something is in motion. Okay. Both of those are a frictional force that will play into this. If it's moving, this would be kinetic, and if it's not moving, this would be static. Between those two, the static is always greater. It's harder to get something moving than to keep it moving. So when your car dies, you need like the 5 guys on the block to come over and start it moving. But once it's going, you can pretty much just step out your driver's side door and push it yourself. It's amazing. It also has wheels, which is helpful in friction force, right? Okay, so let's actually start with the problem. Here we go. Question 6 says a child applies a force of 20 newtons on a box. We already know this is going to be our FT. They're telling you that's how much they're pushing on a box. And this box weighs 10 kilograms. And it is accelerating at 1 meters per second squared east. Oh, did you hear that? There was a direction there. Okay, directions trip everybody up, but that's what makes acceleration a vector unit, not a scalar unit. Now mass, this doesn't have a direction, so it can be scalar. It doesn't matter what direction the 10 kilograms is. It just weighs that much, okay? That's the mass. All right, so it's 10 kilograms. That's its mass. I'm just going to write this up here as a reminder. Thank you, Newton. 10 kilograms. Acceleration is 1. I bet you guys can do this in your head. 10 times 1. We have 10 newtons. Now, but the kid's pushing at 20. Right? So where is this happening? It says, what is the friction force opposing this child? It's accelerating, so we know it's moving. So this is going to be a friction force here. And since it's moving, we could say this is kinetic. Oh dear, spelling horrible, guys. Okay, so if they're pushing at 20, we're going to subtract 20 is going to be equal to the applied force. Oops, this is the applied force, my bad, team. The applied force, subtract the friction force, is going to be equal to what we have here, which is 10. This is actually your total force, this guy. So it's 20, subtract something is 10. You can probably see that one, right? 20 give away 10 is going to be 10. So this kinetic friction force is also going to be 10 newtons. So if you wrote 10 newtons, you're close. It's 10 newtons, and this is accelerating east. So which way would the friction force be applied? It would be west. 10 newtons west would be a complete answer. Okay, let's do the next one. Number 7, we have a girl pushing a rocking chair across the floor at a constant velocity east. If the static friction between the chair and the floor is 12 newtons, while the kinetic friction is 7 newtons, what force is the girl exerting? So it told us our 2 frictions, but it didn't tell us how much she's pushing. And they don't need to, because is there a net force? Is there any acceleration in this problem? The first line says constant velocity, so there is no acceleration. So her push is exactly matching the friction force. So now we have to figure out, is it the static friction or the kinetic friction? Now it says she's moving at a constant velocity, which means something is moving. She's pushing the chair and the chair is in motion. Therefore, her force must be matching the kinetic friction. And the friction force, which is kinetic, is 7 newtons. So this girl must be pushing at 7 newtons. And if the chair is moving in the east, she must be pushing at 7 newtons east. Okay. Number 8, this might get a little wordy, so stick with me, read along if you have the worksheet, okay? In order to get a 20 kilogram object moving to the west, let's just make our object, okay? This is 20 kilograms, and we want to move it west. In order to get it moving west, a force of more than 30 newtons must be applied to get it moving, okay? Once it's moving, however, a force of only 22 newtons will accelerate the object at 0.2 meters per second squared. Oh dear, my typo on here. This says to the south. That's not helpful. We're going to have to keep that to the west. I don't know how it changed direction on us all of a sudden. We'll fix that. My bad. If yours already says west, I fixed it. Good job. So what is the force that the static friction can exert on the object? Static. So nothing is moving. It's static. It said in the very beginning, it took 30 newtons to get it to move. Which means it needed to be opposed, equal and opposite, with 30 newtons of a frictional force, and that is your static. So the first part of that answer is 30 newtons of static, and this is heading west, so this would be east. Okay. Now we need to find our kinetic, and this is a little more steps to it, okay? Because whatever the static is doesn't necessarily dictate what the kinetic is. We got to find it ourselves. But we've got a 20 kilogram object. I'm going to get rid of this, folks, because now we're going to make this thing accelerate, and it is going to accelerate at 0.2 meters per second squared. That 0 goes with this here. 0.2. 20 kilograms at 0.2 meters per second. So we're going to multiply those because we have force equals mass times acceleration. We want to know how much force is happening here. If that's the acceleration. So we've got 20 times 0.2, which gives us 4 newtons west. That's what's happening. Okay. But what it said was that it took 22 newtons to make that happen. So somebody had 22 newtons of the force applied. Subtract an unknown kinetic friction is equal to 4 newtons. Okay. So 22 minus something is going to give us 4. Well, we could subtract 22 from both sides and take the negative, or we could just move our 4. 22, give away 4. This number has to be 18, which means our friction force, kinetic friction force, is 18 newtons. We're heading west, so this must be opposing us going east. This is my slug bug picture from number 9. In order to get the small slug bug moving, the man had to exert 120 newtons of pressure. However, once it was moving, the man only had to exert 35 newtons of pressure to maintain a constant velocity. So what is the static frictional force? Well, equal and opposite. To get it moving, he had to apply 120 newtons. So he had to be opposed in the opposite direction with the same amount. This means our friction force when it's static was also 150 newtons. Okay. Now, once it got moving, now we're moving at a constant velocity. It's 35 newtons heading in this direction. Now it's not accelerating, so there's no net force. Constant velocity, which means that the friction force, now at this point, its kinetic friction force is equal and opposite. If we're 35 this way, it's going to be 35 newtons in the opposite direction. So our static friction force is 150 and our kinetic friction force is 35. All right, I hope we're tracking here. Next one, number 10. We have 2 students and they're helping to move a very, very heavy science table. This science table is 600 kilograms. That's really heavy. That's like over 1,200 pounds. So it's not real. So we have a 600 kilogram science table and they're moving it around the classroom. And the first student, let's call this one, is exerting 200 newtons. They're heading east, right? And the second student is exerting 175 newtons, also east. We're going to call this direction east right now. If that's tricky because I keep changing directions, I'm really sorry. I don't really have a concept of, I think behind me is north as a reference, but so this might be accurate. Okay. So we have 2 students pushing this table and the table is accelerating so the acceleration is 0.15 meters per second south in the east direction. Again, it's a vector, so we're having directions all the time. They're super annoying. I totally get it. Just try to track them with me, okay? So what's the kinetic friction force between the table and the carpet? Woo! Okay, we have applied force. So we're going to have the applied force subtract the friction force is going to tell us what our total force is. Now our total force is also equal to the mass times the acceleration. So we can figure that one out. The applied force is going to be these 2 guys added together and the friction force is our unknown. So let's start with our applied force because that's the easiest. 200 plus 175. So we have 375 newtons of pushing pressure heading east. And we're going to have to get rid of some friction here. So we've got an unknown friction. I'm just going to move the table. And that's going to be equal to our total friction. So that we also find out by F equals M times A. Our mass is 600. I have to do this on my calculator. This one is a little trickier. I don't know if you can even see. So we're going to do 600, typing it in here, times our 0.15. That is our acceleration. Oh, can you even see that? I got a 90. 90 is our total force over here. So this is a 90 newtons east. And this guy must be east, which means our friction force, gosh, he's got to be west. All right. 375 give away something equals 90. Well, you could do it the other way around to say 375 give away 90 equals our something, right? And that is 285. 285 newtons west is the kinetic frictional force between this table, and it must have some seriously wavy carpet because that is a very, very high kinetic friction. Okay. If you have any questions, please reach out.